Hi, my name is Sarah Baxter, and I will be recapping the Euler angle rates part of the April 27, 340 lecture. First, this is a reminder to complete the course evaluation for this class online and send it in. In the last class, we discussed Euler angle rates, which are the angular velocities denoted by omega. We need to know these because they show up in the Euler equation. Looking at the coordinate frame drawn up when we covered the 313 sequence, the notation for each coordinate system will be denoted by their x-axis. For example, the inertial frame would be denoted by the capital X, the intermediate coordinate system in red would be denoted by x prime, the intermediate in green by x double prime, and the body frame in pink by x. The angular rates can be expressed using these angles defined previously. The omega from the inertial frame to the first intermediate frame is expressed as phi dot either in vector form about the capital Z axis or the Z prime axis. Similarly, between the other frames, omega is expressed as shown. It is important to note, however, that to use these in the Euler equation, they will need to be expressed in the body frame.
I'm Elijah Weinstein, and we're going to be finishing up the recap video for last lecture. Now that we have all of our angular rates, we need to define them in the body frame to use Euler's equations. Notice psi dot is already in the body frame. To transform them to the body frame, we will use rotation matrices. For phi, you can use these two rotation matrices to bring it to the body frame. However, if you started in the inertial frame, you could use an additional matrix, but this is simpler. For theta, you will use only one rotation matrix, and you'll get this expression. Lastly, you can bring them all together with this equation, just combining all the different angular velocities to get one angular velocity from the inertial reference frame to the body frame. Next, we will review the flip-top gyro. Part of the gyro can be modeled as a sphere, which does not have an intermediate axis because of its complete symmetry. So, if the gyro is spun, it can overcome the friction and end up on its head, like this. Lastly, for Euler angular rates, recall that we had these three expressions for angular velocities. Now, we want to solve for phi, theta, and psi dot so we can integrate and get equations for the orientation of the rigid body. To get this, we multiply wx by cosine psi, and then subtract wi times sine psi. Then a bunch of stuff cancels out and yields this expression. A similar process can be done for the following two expressions. Lastly, we can rewrite these expressions in terms of theta, phi, and psi dot to solve for our angular rates, and then these expressions can be integrated to find the orientation of the rigid body.